Hi, everyone. Welcome to today's Gifted World Masterclass. I'm Siddharth. I'm one of the community managers of www.giftedworld.org. We are an online community that started in January of this year. Our goal is to provide a space, a support for students, parents, and teachers to achieve their full potential. We conduct free masterclasses. We have a whole range of resources on our website. And very soon, we're going to be announcing a series of online courses that are designed to engage students of different age groups, ranging from classes 5 through 8. Thank you very much for joining today's session. Today, we're very excited to be hosting Professor Sukanya Sinha. So I've known Sukanya for about the past year. We've worked together with teaching some students, getting people to do things like count how many hairs are on your head, how many leaves are on a tree, and making people think that that a computer is reading their mind, whereas in fact it's just doing simple mathematics. And she's someone who has spent a career really making science and mathematics fun and engaging for students to learn. So I'm really thrilled that she's conducting today's webinar. Sukanya has been a teacher at several GenWise summer programs. And if you're unaware of these are summer programs that happen every May and July in Manipal. I'll be sharing links about it later. She's also doing something very special next month, which is she is going to be teaching a summer program in East Africa. So this will be for students of grades 8 and above. And it will be happening at the IIT Madras campus in Zanzibar. So I will be sharing links of all of these towards the end of the session. But for now, I'm thrilled to welcome Sukanya to take today's session. Please note that there will be specific times during the session where we'll open it out for questioning. At other times, I request that you keep yourself muted. And I will help. Anytime you have questions, put them in the chat box. We will definitely go through all the questions that come in the chat. And apart from the times where we open the floor out for everyone to ask questions. So with that,
sometimes I'm not able to see the chat questions, and some chat questions one might even answer later. You know, there may not be time, so we'll see.
But I'll make sure that we take care of the chat questions. So don't worry about your questions getting missed.
Okay.
So with that, onwards to today's session is titled Secrets of the Stars, Discovering What They're Made of. And I'm very excited to hand it over to Sukanya. Thank you so much for coming today.
Thank you so much for inviting me. And I'm excited to talk to all these young people about it. The age group that I sort of had in mind was a little older maybe, but let's see how it goes. I mean, it's nice to see like so many enthusiastic faces from all over India, and so many from Dubai and Sharjah. So one problem is that when I'm going to share screen, so then I probably will not be able to see your faces. So that's a different. So Siddharth will manage that.
Yes.
So before I start the share screen, let me tell you that when I gave this title, I hadn't really fully thought of what I'm going to talk about. Like it's so I just gave they made up an interesting title, and then I started thinking, what am I going to talk about? I'm going to talk about what stars are made up of. But really, what I intend to do is tell a story. Tell more than one story maybe, because very often when you're studying something, especially science in school, you're given like maybe one line about, this is a law that was discovered by Newton. And you get the impression that, he just got it in a day and, he got it right at the first go. But that's not the real story behind science. You know, there are lots of blind alleys. There are lots of people working together, struggling, collaborating, not being able to figure out something for decades. Whatever you see in a line in school, maybe it took 50 years to figure it out. So I'm going to talk a little bit about, I'm going to tell that story, and specifically about, you know, how we found out what stars are made of. Okay. So some things you may not be familiar with, so you can ask, and some things maybe even if you haven't heard the names, you'll find out later. So I'm going to share screen, and here we go. All right. So, okay, this one goes up there, that slideshow. Where should I put it? Yeah, that's fine. So if I do the slideshow, it's better, but you know, I don't see the faces, but I think I'll try that. Does the slideshow work? Let's see. Okay. Yeah.
Yes,
Okay.
it's working.
Okay, so this is the title of it. So first, it's the secret of the stars, discovering what they are made up of. So first, we are going to look at the star closest to us. And I'm sure, like all of you know, which is the star that is closest to us. It's like a very familiar star, and that's the sun, right? So that's our nearest star, and it's actually nearest, but very far away, because it takes light, which is the fastest thing on Earth. It takes it 8 minutes to get to us. You know? So it's 8 light minutes away, and it is 150 million, 152 million kilometers away from us. You know, so it's like very, very far away from us. So now, if one asks the question, so now before that, if one asks this, tries to ask the question that, you know, what is the sun made up of? If I ask the question, what is the earth made up of? That's not so difficult. You know, I mean, it is still difficult, but, you know, you dig up stuff at various places of the earth, and you find out like what elements make up the earth, you know, what's the composition, you take samples. But here's the sun, which is 152 million kilometers away from us. And even if we were to able to board a spacecraft and go there, you know, it will take, well, it will take, it's not going to take your lifetime, but it will take a long time, but it's possible. But it's extremely hot. You know, who's going to go and dig up the sun in that, you know, 6,000 Kelvin temperature? And it's impossible. You're going to melt away to nothing. So that's not a possibility. So it's a very, very amazing thing that scientists even you know, dare to ask this question, that there is something 150 million kilometers away, and yet you want to find out what it's made up of. It's not accessible to you. You can't just go there and pick up pieces of the sun and analyze it. So how do they do that? What do we see from the sun? What is it? Of course, every morning the sun rises, and uh, we get light from darkness, and it also gives us heat. You know, it's like the source of life on Earth. So what we see from what is accessible to us from the sun is the light, right? So we all, I mean, there's plenty of sunlight. So that's the only thing that comes to us from the sun. So whatever we want to learn about the sun, that's the only thing we have access to, right? So whatever we want to find out has to be decoded from sunlight. And how do we do that? That is the story, and what people did about it. Yeah. Okay. So let's see. So here, now sunlight, everybody knows that sunlight is made up of light of different colors. So sunlight, when we look at the sun, we see just white light, at best bright yellow light. But even before scientists started messing around with it, people saw rainbows. So we knew that, you know, sunlight is not so simple. It's made up of several colors, and we know that violet, indigo, etc., etc. All of that we've seen in rainbows. So now, but one wants to have a little more control over analyzing light from the sun. So as I said, like we're trying to look at all the information that we can get from the light from the sun. So we can't just sit around waiting for rainbows. So scientists want to design experiments so that they have control over the thing. And along comes, so everybody has heard of Newton, I suppose. Have you all heard of Newton, more or less? Can I see a show of hands? Yep, okay. So here is Newton, and this is way back in 1660. So what he did, he was in a very dark room. He had a tiny little slit, and he had this glass contraption called a prism, which many of you might have messed around with or have seen. And what he did, he let a beam of sunlight come through that hole, and he passed it through this prism. And what happened is that this broke up into so it broke up into all these colors, like the rainbow colors, and that you could control. This is something that and so knew that whatever the sunlight is made up of, it is actually made up of various colors. That's what Newton said. And when I say that, so I wrote this word in red because this is something that's going to come over and over again in our story. So Newton in 1660 produced a spectrum of sunlight through a prism. So basically a spectrum means that whatever light you get, you're breaking it up into its components, so it's creating a spectrum. So now, so that was a long time ago, 1660. So cut to, see what happened. So this is what happens, like, I don't know, like, yeah. So what did Newton wrote a big book called what he called Optics, and he spelled it funny. Those days that was the spelling. But what he says that if sun's light consisted but of one sort of rays, there would be but one color in this whole world. So that's what makes the world colorful. Okay, now later in the so this is many centuries later, in the 1800s, it was established that light is actually made up of it's a wave. And different colors correspond to different wavelengths of the wave. And a wavelength might be a new word to some, a familiar word to some of you, but basically it means that a wave is, like it goes like that, and there are crests and troughs. So the distance between two consecutive crests or troughs is what characterizes a wave, and it's called a wavelength. And each color, rather than saying that, it's breaking up into different colors, it actually, now you can do a little better and say that each color has a specific wavelength. Not only that, there is an advantage because after the human eye is not that sensitive. I mean, with what I see as yellow, maybe different shades of yellow, which my eye may not be able to detect, but something that detects the wavelength for every characteristic color, there will be a separate wavelength, so here and the wavelength is very, very tiny. So this is like 400 in nanometers. So it's like 1 divided by 1 followed by 9 zeros. That's so it's 400 nanometers. So that would be 1 divided by some 7 zeros, 1 followed by 7 zeros. So it's very, very tiny. Okay, so now in 1814, almost 150 years after Newton, there was this German physicist called Joseph von Fraunhofer. So he looked at the sunlight again with a more sophisticated instrument. It was of the nature of a prism, but he got it. He had like they were 150 years that had gone by. The instruments became more sophisticated. And he looked at the solar spectrum again in greater detail. And this is what he saw. So it's like shades of different shades of violet, much more detailed than what Newton saw. And which is all fine. Different colors. So it's like moving from, purple to blue and aqua and orange, etc., etc. And he also detected figured out their wavelengths. So the wavelengths are also written below. And he gave them several names to classify these colors. But what was strange, what Newton could not see, was that amid these lovely colors, there were these strange dark lines, you know. So there were these dark lines, and that Fraunhofer found, and he had no idea what they were. And so this question was a very uh, pertinent and worrisome question that, okay, light is coming from there, but why do we see dark lines? And the interesting thing is that, or the amazing thing is that people worried about it, and they worried about it for 45 years before they got an answer. So that's what I was telling you about, that, you see something, and now in the book, you might see the next line says that this is the solution. But it took, many, many scientists, decades of, sleepless nights to think about it and figure out, worry about what these dark lines were. So, as I said, this is a story, and this is like a detective story. Scientists are detectives where they are trying to figure out things from, these are this is the spectrum is the clue that nature is giving us, and we're trying to figure out the whole story from just seeing, limited amount of information, clues. And here, I mean, one could pose this question as that who stole these light? So who stole this light? Like the thing is that they normally, if you had from the prism spectrum, it looked like everything was bright, and looks like somebody has taken away pieces of light out there. So that's why you have dark lines. Okay, right. So Fraunhofer's, as I said, Fraunhofer's dark lines remained a mystery for over 4 decades. 40 years people were worrying about it, not getting an answer. Everybody had a different theory about it, and they were not agreeing with each other. They were inching towards, the whole picture, but it was not at all clear. What it remained a mystery. So as I said, science is like scientists are detectives solving a mystery, and they keep at it, like they're not, and these mysteries are like very long-term mysteries, not something that gets solved in, like a week, 2 days, whatever. Yeah. 4 decades. Then what happened? Then there were these two guys called, they were also German, Kirchhoff and Bunsen, and they were two scientists, German scientists, and some of you, I mean, who have studied a little bit more advanced physics might be familiar with Kirchhoff's laws of circuits. And Bunsen invented this burner that is used, gas burner that is used in chemistry labs regularly to test substances, to do various things. So that's a standard attachment of equipment in chemistry labs, and he invented it. So they were, and those were the days. Now you have very rigid divisions between physics, chemistry, biology, mathematics, etc. But in those days, I think people moved a lot more easily between physics and chemistry, and sometimes mathematics as well. So what these guys discovered, they had this Bunsen burner, so they had a very nice way to produce a flame. And what they used to stick substances into the flame, and notice that all materials radiate in certain characteristic colors when hot. When you heat an element, it gives a little, gives a particular colored flame. And when you are older and you are, I don't know, 12th grade or 11th grade or something like that, in the chemistry lab, this is, you'll do something that is called a flame test, that you're detecting something by looking at what kind of color it's giving, the substance, because the substance radiates with a characteristic color. So for example, you may not, sodium burns with a yellow flame and copper. So whenever you have something, material containing sodium, if you put it in in that burner, it's going to burn with a distinctive yellow flame. Copper will blow with a blue-green flame, and so on and so forth. There are various, so it's like a signature of whatever material you're putting in there, whatever element. It's got to, when it's getting very hot, this is the way it glows. So I don't know about, now they don't have so many of them, but when we were growing up, there were street lights which were sodium lights, sodium vapor lights. And they were, glowed very, they had a very strong glow with great intensity, and they were yellow. So this is a characteristic, and the sodium yellow will be an important element in our story. So just keep. So these guys worked together, and they were in the University of Heidelberg, and this was around 1860. Actually, this was what I'm talking about is 1859, close to that time. So, and they used an instrument called a spectroscope, which was like became more sophisticated than Newton's. And this is like an old picture of a spectroscope. It had a prism, but it had various other attachments so that you can measure wavelengths as well. So finer divisions. So you could measure the wavelength of light, and you could produce a spectrum, measure the wavelengths, and rather than just observe colors. So here is this guy where he's trying to find out what wavelengths or what colors are in that light from the flame, and he's looking through that, looking through the telescope out there. Okay. So these guys had a good spectroscope with them, and as a matter of fact, I think Kirchhoff invented this spectroscope. I'm not 100% sure, but like he was one of the pioneers in building this instrument too. So they had a lot of fun with this. Once they got the spectroscope going and this realization that every element has a characteristic spectrum, they kept looking at various flames and, like finding out what their spectrum was, what was in there, and detecting things. Okay. All right. So next, so what these guys found in the laboratory was, and those days, so since the spectrum was how the light split up into the colors or the wavelengths was a signature of the element, so these guys using the spectrum, Kirchhoff and Bunsen, they actually discovered two new elements which were not there, which had not been discovered before, rubidium and cesium. Yeah. But what they've observed, playing around with this, was the following: that you had white light, yeah, and if you had a white light, and this is the source of white light, strong white light, and then you looked at its spectrum through the spectroscope, you see a continuous spectrum, like we saw, like the blue, green merging into the yellow and all that. And then if you had just a flame and you looked at its spectrum, you saw this, say you took sodium or whatever, some element and some material, and you looked at its, analyzed this flame of the, spectrum of the flame, you saw these discrete bright lines, like not continuous, like specific lines. Here you have like two violet-like lines and a blue line spaced from a darkness in between and all that, bright line spectrum. This came from the material or like the gas above this, hot gas above the flame. Now, then what they found, so these were two separate things, directly from the bright white light, this is the kind of spectrum you get. From a specific element or a specific material that you hold in the flame, this is the kind of spectrum that you get. Now, they thought that what if we could combine these two together? And what they did was to cool down the gas a little bit, and then now pass the light, the bright light, the white light through that gas. And lo and behold, what did they see? They saw exactly what Fraunhofer saw. They saw the same kind of dark lines that Fraunhofer saw, and when they looked at the position of the dark lines, they saw that they coincided exactly with. If you superpose this bright line on top of this spectrum, you would find that the missing colors are exactly the ones that would come only from the gas, only from the gas. So that sort of, opened up a whole new game, in the sense that they understood, and this was called the absorption spectrum, because what they found is that when you heat up a gas, can you hear the sound? Because she's working in the kitchen. Is the sound?
No, you're clear, Sukanya.
Okay.
I think it's clear.
So the thing is that what happens is that now if you, So if you have if you heat up the gas, it emits radiation, and it emits radiation which is characteristic of that element. And so you see this bright line spectrum. This is called the emission spectrum. Now, if you take the white light, pass it through the slightly cooled gas, what you see is this with the black lines, and this is called the absorption spectrum. Okay. So, and the missing lines sort of just fit with this, they just fit. Okay. So I see a lot of questions on the chat. So should I pause here and ask? So there are 24 questions. So
no, not that many questions in the chat.
Okay.
I just,
so all right. So
yeah, but maybe we can pause and ask anyone to raise their hand.
Yeah, the 2 minutes I'll pause and ask if somebody has a question.
So feel free to raise your hand and ask a question.
Okay. If Dhruv.
I didn't understand the part where you said about the process of finding the spectrums.
Process of finding the spectrum. So the thing is that, so if you take white light or whatever source of incandescent light, you pass it through basically you're looking through a spectroscope. You're putting it through a prism, just like Newton, and the white light produces this kind of spectrum. It's breaking up that light into the colors, like this, and the colors are sort of continuous because they are, one merging into the other. Now, if you're looking at not a white light, but a specific material, say you're putting sodium into the flame, and there is a gas above that, and you're looking at that light coming from that flame and putting it through a prism. You see a very different kind of spectrum where it's not a continuous spectrum and not all colors appear. Specific colors appear as discrete lines. That's one. And every time, this one also you're putting through a prism, and that's how you're resolving the spectrum. Next, what you do is you take the white light, you pass it through this, whatever that material that produced this bright line spectrum, slightly cooled down. And what it does, it absorbs only the lines that it emitted in that bright line spectrum. So those parts, so so these are these characteristic lines, the emission lines. Once it passes through this, it selectively absorbs only those that it could emit when it was very hot. Yeah. So that's what's producing the right. And every time you're passing it through a prism, roughly, spectroscope. Yeah. Does that answer your question somewhat?
Yes, thank you.
Okay. Adya?
Yes, actually, I have two questions. One, what is the spectroscope and spectrum?
Okay, spectrum is that the word, it's a new word. Spectrum is basically, if you think about breaking up light coming from any source into its components, like different wavelengths. It's actually a mixture of different wavelengths of light. Like I started with a rainbow. So you take white light from the sun, it's bringing up into several colors, so that's what, and that array of several colors that you see beyond the prism, that is called the spectrum. Yeah, that's what's called the spectrum. Yeah. Is
And
that
the spectroscope?
a spectroscope is this contraption where notice that there is a prism out here, right? And there is a source of light, right? This is a flame. So this source of light is directed towards the prism, and it's actually breaking it up into different colors. And then this man is looking through a telescope to see what, or some eyepiece, to see what colors. So this is going to show up in his field of view. It's a machine to resolve the spectrum, right? Look at the break up light into different its components. Okay, so it's just a machine. Yeah, or it's an instrument. Yeah.
And one more
Sahana?
question.
Yeah.
I didn't
Yeah.
actually understand how you got the bright line spectrum. Only just the bright
Bright lines. So this is So this is something that they just observe. They took say you take some material, you put it in the flame. Okay, it's not just a flame. You're putting a specific material into the flame, and it's burning. It's once it's heated up, it emits light with its characteristic spectrum. Like so. Then once you've put in, so if this guy was watching the flame, what he put in the flame, actually his assistant would have put some say copper into the flame, and then he breaks up, he sees like how that copper, the light emitted by copper breaks up, and what he would have seen is like, say for example, these two blue lines, for example. Or so whatever material is going to produce an emission spectrum. It emits light, but that light is a very specific kind. Every material will have its own set of lights, and from the lines you will learn what the material is. Okay. Yeah.
Okay, thank you.
Yeah. Some more? Sahana, so I'll take two more questions so that I can, then we'll break again. Okay, so I have, Sahana, you had a question?
Yes. I have a doubt on what you explained right now, the slide, because I couldn't understand how the black lines appear in the bright line spectrum.
How the black lines appear. So what happens is that the these are three things happening, right? This is a white light, which is producing this kind of spectrum. Then this is this cloud of gas, which is like heated up in a flame, or whatever material, it's like turned into gas and hot gas, and it's producing is, then you put it, then you don't keep the white light there. This is separate. You're just looking at the cloud of gas and its emission spectrum. So only giving you bright lines, but not like continuous. They're just giving you specific lines. Okay. And now you combine the two. You cool down the gas a bit, and it's going, and you pass the white light through the gas, cool down gas, and now you put your prism in the path after that, and this is what it's producing. And you find that when it was hot, whatever light it emitted, precisely those it has absorbed. That's why those lines are missing from this bright light spectrum. Yeah, so that's what's happening. Yeah.
So you're saying that when it's hot, the bright line spectrum is what comes out. But when it's cold and you pass light through it,
Passing white light through it, yeah.
those same lines are what it's absorbing and not letting continue.
Yeah.
So only things that it gas doesn't absorb what makes it through.
Yeah. So if it's absorbed, it's not, if that part of the light, those wavelengths of light are absorbed, they don't get through, right? So that's why you're seeing dark lights. Yeah. Okay. So I'll take just one more question. Yeah. No, two more. Let's see. Jagat.
Yeah.
Ma'am, a cloud of gas meaning, ma'am, which, ma'am? Cloud of gas meaning, I didn't understand.
Yeah. So this is a little vague because this is because I got I had to pick pictures of the internet. So if you think about it, and the cloud of gas will be becoming very real when we talk about the sun. But basically, imagine where the cloud of gas is. I put that Bunsen burner, right? And I make a flame, and then I put some material in it, right? I put some, say, copper wire in it, and the copper wire gets very hot, and it almost becomes it becomes in a gaseous state, and when the and it starts emitting light, right? So that particular material, yeah, so that's what's actually the cloud of gas
So,
out there.
ma'am, when light pass through the cloud of gas, meaning will it be the atmosphere if it is in the prospect of the sun?
Yeah. So we'll talk about the sun later. So before we got to the sun, Bunsen and Kirchhoff were just testing with a little burner, and they put copper, sodium, all these materials in it, and found out, like, when they get really hot, what is the light? What the light coming out of them? What does it? What are the components? That's what they would.
Okay.
So this is a little, misleading, because really this is you sort of replace it. If you look back on it, this is sort of the flame with some element, or like some
So,
material.
ma'am, the cloud of gas will be in the tube or something.
No, it will be not in the tube, right outside the flame. Right outside the flame. That's where they will see. That's where the hot. It will be basically a hot material. Yeah.
Oh, okay.
Yeah. Okay, I'm going backwards. Yeah.
Okay, ma'am. Thank you.
Yeah. Krishana.
Yes, miss. Yes, miss. So, I have a question. I know that the bright light spectrums, those lines that we see and the dark lines match, but are they particular, and do we get the same ones every time we look, or are they different?
No, so if it's the same material, that's a good question, because if it's the same material, every time we will see the same spectrum, because it is just like, it's a signature of it's nearly a fingerprint of the material. Just like every human being, I've also said that on a slide, every human being has a unique fingerprint. That's how they identify you. So
every different material has a
different spectrum, and it's characteristic of that material. So if you put the same material in the flame and observe it, every time you will see the same spectrum, and that's a very important thing. Okay, so now let's close the questions and and go on, and we'll
Like, by different spectrums, you mean we mean different places of light, right? Like those lines would be in different places, right?
Yes, and different places, and there will be different colors. Yeah, there'll be different colors. Say for example, if I put sodium, nothing will be here, and I just see two yellow lines. Or I would see, I put some other material, I might see another violet line out here. So it will be different places, different colors. So it will have a characteristic pattern, just like a fingerprint in some sense. Yeah? Okay.
Okay, thank you, ma'am.
Yeah. Okay, so now let's. So this whole idea of finding out elements or what things are made up of is called, from the spectrum, is called spectroscopy. And spectroscopy revolutionized physics and chemistry. So as I said, the emission spectrum of an element, when you heat an element, what kind of spectrum it gives out, was recognized as a kind of unique fingerprint of an element, right? So scientists were the detectives, led to new discoveries from the clues found from the spectrum. So this is your fingerprint, just like detectives find out, like, whose fingerprint is it from the fingerprint. Scientists were looking at all they had access to, like if they have if they didn't tell you. So for example, here they put in copper, and they saw the emission spectrum. Now, if you turn the question around and say that I'm not going to tell you the copper, that it came from copper, I just give you the first spectrum. Now, can you tell me like what produced it? So you're asking for the reverse question. So that's what spectroscopy is about. You look at a material which is an unknown material, you put it, you have a set of known materials which produce a certain kind of spectrum. Now you take an unknown material and you see a new spectrum, and you think of, what it is, you try to think about. So you might find a material which is a composition of different known materials, or occasionally you might discover a completely different new discovery, a new element. And that's what we will also get to. So these guys also, Kirchhoff and Bunsen, in this process, they heated up various materials and looked at their spectra, and they found two spectra which did not belong to anything that was known on the Earth. So they realized that those were completely new substances, new elements, and they had to give them new names, and those were rubidium and cesium. And the whole discovery came from spectra. So that's a very, very powerful. So it's really mapped to a complete detective versus fingerprint story. Yeah? Okay. No, but now we had started out talking about the sun, right? So what happened to the sun? So we stopped talking about it. So now what about the sun? So here comes the sun, and so here there's a little story out here. So what happened was, so in the 1850s, this Bunsen and Robert Bunsen, they were great buddies and were scientists that were working together. Kirchhoff occupied neighboring physics laboratories at Heidelberg University. So one night, Kirchhoff and Bunsen were watching a fire in Mannheim. Mannheim is like few kilometers away from Heidelberg. How far away is it, Utpal? Mannheim?
About 30 kilometers.
30 kilometers. So 30 kilometers away from Heidelberg, and the fire was so bright they could see it from Heidelberg. But now this whole thing was a addiction. Looking through things through light through a spectrometer was like a game and an addiction. So they said, like, we have to look at that fire. What is that fire made of? So they looked. So they had a telescope and they watched the fire in Mannheim from their laboratory window, and then they looked at the spectrum, and they knew what the spectrum of barium and strontium looked like. These are two different elements. And they saw those lines in that spectrum, and they knew that they were barium and strontium and whatever was burning. I don't know what exactly was burning there, but they figured out. But then a very important realization dawned on them. Then later, while out walking, Bunsen remarked to his colleague, if we could determine the nature of the substances burning at Mannheim, which was 30 kilometers away, why should we not do the same with regard to the sun? Because that's far away. And, we determined the composition of something that was far away, 30 kilometers away. And without actually bringing samples of it and putting it in a flame in the laboratory. We did it from a remote location. So that's 30 kilometers away. Okay, the sun is 150 million kilometers away. So maybe this applies to the sun as well. So then they said, but people would say we must have gone mad to dream of such a thing. Kirchhoff replied, and Bunsen, I have gone mad. That's what he said. To which his colleague added, so have I, Kirchhoff. We're just two mad people wanting to find out what's in the sun from the light, purely from the light, purely from looking at the spectrum. So the two scientists would go on to invent a new spectroscope, the Bunsen-Kirchhoff spectroscope, and which allowed them to discover the elements cesium and rubidium from the spectra, which I told you about a little while ago. Okay, now, so what happened here? Sometimes this is not working. I don't know what happens. Okay. Yeah. So I wanted to show this picture as well. So from current slide, let's show. Yeah, and this was actually, it's just a coincidence that Utpal Chattopadhyay, who's here as a spectator today and who gave another masterclass a month ago or something, 2 months ago. He spent like 3 months in Heidelberg. And while he was on a walk, he did not know about this Kirchhoff-Bunsen stuff at all. And he came upon this plaque on a building, which says, my German is like very elementary, but it basically says that in this house, Kirchhoff and with Bunsen, in 1859, they analyzed the spectrum, and I think something about the chemical composition of the sun. So basically, that's where this is what their laboratory was, and he just chanced upon it. So he had taken a picture, so he shared it with me. Yeah. So here this is the first time people thought that this was even possible, and this was not taken very. So this is what the Bunsen-Kirchhoff idea was, that their conjecture, if it's a big word for you. So what they thought about, I don't know, this one. So what they felt, and so one of you hinted at that, and they thought that the form of dark lines were due to the absorption of specific wave, just like we saw in the laboratory. You know, you pass it through a gas and specific wavelengths are coming from the hot source, they are absorbed, and that's what they make the dark lines. You know, their characteristic emission lines are absorbed, you know. So they said that, you know, like maybe from the sun, whatever light is emitted from the region of the light emitting region called the photosphere comes through the cooler atmosphere of the sun, little cooler, you know, like, and as we said, like they also observed that they had to cool down the gas a bit before they passed it through otherwise the emission spectrum comes from a very hot gas. So they said, like, this is what is going to happen. It's going to pass through and this atmosphere, whatever elements it has, if it has certain elements out there, those lines are the ones are going to be absorbed, and that's what's creating these dark lines. So from studying those dark lines, so that's what's happening, you know. So just like you could figure out, like from that missing light, matching that to the emission spectrum, you could figure out what elements should have been there, you know, if it passed through unhindered. So you would be able to discover the composition of the solar atmosphere. Okay. So they predicted, but there was a catch to this, because they predicted that if one could isolate the emission spectrum coming from only the atmosphere, the corona, the reverse spectrum will show up with bright lines appearing in the exact positions of the light line and the dark lines. That will also reveal the chemical composition of the atmosphere. So let me just go back a couple of slides. And as usual, this is, I don't know, something happens. So yeah.
So just press the up arrow, you'll be able to go back.
Yeah, so I'll just go back here. And basically, now let's think of this as the photosphere and this the atmosphere of the sun. And what will happen is that without this, it will have some spectrum. Now it has to pass through the atmosphere, right? And if it has to pass through the atmosphere, the light we are seeing in our on Earth, this is what we are seeing with the dark spectrum. But if we were able to somehow isolate only the emission spectrum of the atmosphere and see this part, the bright line spectrum, we would know exactly. So what would happen is that if we were able to isolate this, we would see the reverse spectrum. You know, basically dark, where everything that's not here would disappear and only the bright lines would appear. So that was their idea. But how to do it? You know, like every time we see the sun, it's like bright light is coming through the atmosphere. How do we just look at only the light coming from the atmosphere? So that's kind of crazy, yeah?
Shall we ask the students if they have an idea?
Yeah, do you have any idea? Like, how would you do this? You know, we're getting everything as a package. Everything's coming on only from that. So how
can you repeat the question?
So what I'm saying is that I went back and I showed you that
Yes, ma'am.
to see the emission spectrum, the part that is coming only from the atmosphere, because then we will see the missing lines, right? That's the complement of this, right? That will be the bright lines, which will not. But so for that, so to put the two pictures together, I need to find out the spectrum of light coming from only the outer atmosphere. I have to cut out this light from the, coming from the photosphere, from the inner parts of the sun. But when we look at the sun, this is all we see, right? This is what we are getting. So how are we going to isolate light from there? How is it possible? What can we
Excuse me,
do?
ma'am. Actually, I couldn't understand this slide at all.
Okay, so what I'm saying is that there is, there is a region of the sun which emits the major part of the light, which is called a photosphere, and that is emitting like bright white light, and then if that is passing through there is an outer layer of the sun, which is the atmosphere, which has a combination of gases which people didn't know what they were made up of. When it's passing through those gases, that atmosphere, it's producing this Fraunhofer spectrum, which has dark lines. And we just saw that the dark lines are due to whatever material in here is absorbing that part of the light that it would emit if it was left to itself, just if you could isolate that part, right? The problem is that we are seeing, yeah, Adya, was that a little clearer?
Yes, ma'am.
Yeah.
It says that we see this, but like I don't really understand how we can see that, because when we see things on Earth, we see them as specific colors.
No. When we are seeing sunlight, and so when you see this, we're not looking directly at the, so these are good questions. We're not looking directly at the sun, but we're looking at the sunlight that is coming to us through a spectroscope, right?
Okay.
So that's the thing. So it's not like what we're seeing. Our eyes don't have that resolving power. So this, when I say see this is something you're seeing on Earth through a spectroscope. Once you put a prism and see this, yeah. So that's what we're saying. It's break.
So, ma'am,
Yeah. Somebody was saying something.
There is a comment. Divya Arun says, "Can you create some kind of a filter that would block out the atmospheric effect?"
Ah, very good, very good, very good. So that's a very smart idea. It's a good idea. That can we create a filter that blocks out the photosphere light and just isolates the atmosphere. Yes. Any other ideas?
There's also a statement that from Keshav saying that could other animals which have very different vision see something different from us?
Yes.
That's also possible. Like for example, we later will come to it because we are not seeing, our eyes are sensitive only to the visible spectrum. For example, snakes can
ma'am,
actually quote unquote see the infrared part of the spectrum. So
ma'am,
it's possible. Yeah.
ma'am,
But yeah.
what is trying to say is that could they see all this dark lines, some animals which have like different sort of vision, because we humans can only see certain colors without the help of technology and filters.
Okay.
With our
So
naked
I
eye,
don't
we
know
can-
whether there are any animals which can see that. That's an interesting question. Whether their eyes are sensitive enough to not put things to a prism, and whether they can see the dark lines directly. I don't know. I don't think so, but it's possible, entirely possible. We may not know, but it's true. But we poor human beings, we have to take sunlight, put it through a prism, and see these things. Yeah. But that filter idea was very good. Can you think of a natural phenomenon that's going to block out that main light?
So,
A
ma'am,
solar eclipse.
Excellent. And
Yeah.
that's exactly what they were looking for. That's great that you actually thought of that. So before that, let me tell you about this famous French philosopher who was very influential, and is a positivist philosopher called Auguste Comte. And what he said, and his ideas influenced the world a lot. And what he said very confidently, that human beings will never be able to find out the composition of the stars. So since you'll never be able to find out about it, don't waste your time on it, So yet, defying all that, these scientists like Kirchhoff and Bunsen said, we are mad and we are looking for this. Okay? And the other thing is that Kirchhoff and Bunsen's idea was not very well received by astronomers as well, because at that time, as I said, there were blind alleys. People had different ideas which change in science. What was the prevailing wisdom was that the core of the sun was cooler than the atmosphere. And here we need hot gas to pass through a cooler gas. And it was, in their mind, it was reversed. So they said like this Kirchhoff-Bunsen idea can never work. The sun's structure is not like that. But they went on with their thing. Yeah. And then what did they say? So this was 1859 when these guys proposed this theory, so got that idea. 1859 otherwise was also a very important year because that was the year Darwin proposed his theory of evolution, and he wrote his book on Origin of the Species that was published. So now 1859 and this is 68, so 9 years later, right? So look at the perseverance of scientists. How would you? So you make a prediction, and a prediction is not good enough. For it to become truth, reality, you have to test that prediction. And to test this prediction, you had to block out the sunlight from the main source. And this would be done naturally during a solar eclipse. Not only that, you need a total solar eclipse. And it so happened 1868, there was a total solar eclipse, and this is the path of the solar eclipse. And it's a very, light colored picture, but I hope you can see that it goes right across the middle of India. Can everybody see that?
Yes, ma'am. Yes,
Yeah.
ma'am.
It's a French thing.
Yes,
French
ma'am.
So it says Hindustan and, Perse and China and all that. But the path of totality goes right across India. So the thing is that look at this whole story, that though they were sitting in Germany and doing all these predictions, to observe this eclipse, this whole center of the drama became India, because the best path of totality was there, right here. And if you look at it, this is more or less Andhra Pradesh. And the total solar eclipse would be there on August 8, 1868. And all these 9 years, they were waiting with their spectroscopes and telescopes to test this. And so this was the time. So now...
Excuse me, ma'am, I have a question that's
Yeah.
not related to this. The question is, how do people find out that there's going to be a total solar eclipse in the coming years?
So that's a different thing altogether, and that's a fairly
Ma'am, I know this, ma'am.
well understood theory, and I can give you things to read up on it. But this is something, the eclipse prediction now is a very well understood thing, and it can be predicted, and people have been observing the sky for the longest time, and this is a very robust way of predicting it. So they're able to do that. So I'm not going to get into the details of that. Because they know the path of the sun, path of the earth, moon, everything in great detail. So what is that? So we've got like a lot of scribbling. Somebody wants to show that.
Could I request people to not annotate?
Yeah, not annotate on this.
And undo your annotations.
Yeah.
And also, we'll, if it's okay, we'll pause for questions after about 10-15 minutes once Sukanya is able to finish out this part of the story.
Yeah. Okay, so now next what happens? So here there are, so this is like a big time detective game where new actors, and a drama where new actors enter the stage. And the people who they come from all walks of life. So it's so here was, and not all of them, can you ask them to not annotate? Yeah. No annotation. Huh? So here are people who, so let's introduce them one by one. So there's this James Tennant, who was a soldier in the East India Company Army. So he came to fight for the British, and in between, he was also a surveyor. So he was taking part in survey of India and looking at heights of mountains and mapping terrains and all that. But he was also very interested in, so he was a regular soldier because he fought in the Sepoy, important battles in the Sepoy Mutiny of 1857. And but he was very interested in astronomy. So they could do, and he played around, fiddled around with telescopes, and I think he even published papers and all that. So he was, a self-taught astronomer. Then there was this guy called Norman Pogson, who was actually an astronomer. Or those days, astrophysics really had not taken off, because this is the first birth of astrophysics, because astronomy was looking at positions of stars and planets and whatever, but you really didn't worry about, the science going on, the physics going on here, what they are made up of, how they are emitting light. All these questions were, not even thought of. They were. So Pogson was an astronomer, but he was in England, and he didn't get a regular job there, but in a university or anything like that. But he came to India and was in charge of the Madras Observatory. He was the head astronomer of, there was an observatory in Madras, and he also was a meteorologist, so he did weather predictions and all that. That was who he was involved in. He was also very passionate about this thing, and he knew about this, all these guys. So then Jules Janssen was a French astronomer, and he was a well-known astronomer. Though he did not get a regular job at a university, he had friends in high places and was able to get grants and do his observations and all that. He was well known, though he was not a professional in the sense of professor in the university or anything like that, regular job. Okay. So Norman Lockyer, I guess, was the only guy who had, I think, a position in a university, and was a bona fide astronomer who had also had a proper job, astronomy job. So all these guys knew about the Bunsen-Kirchhoff theory and were keen on testing it during the eclipse, right? Now, Tennant was already in India, so he was, and Pogson was also in India. So Janssen had to get a grant and a team and all instruments to come to India to observe the eclipse from France. And Lockyer's story is a little different. He had said that, I have figured out a method. I don't want to go around chasing eclipses all over the world. I figured out a method to test this without an eclipse. So we'll come to that in a while. Okay. Now, so here, so this is like a long period, 6 minutes, 47 seconds of total eclipse, totality. That's a big deal. And Tennant and Janssen, they stationed themselves in Guntur, small town in Andhra Pradesh. Then it was nothing. And Pogson, so Janssen got good grants, and Tennant also, they had instruments and everything. Poor Pogson didn't get, he was not so fortunate. He didn't get an instrument. Somehow got a hold of a spectroscope, and he couldn't become a part of the observation team. But what he did, he chose Machilipatnam, which is coastal Andhra Pradesh, and that I first heard about when this, it's right on the coast, so the tsunami affected it tremendously. Yeah? So what happened is that he was also a meteorologist, so there was a weather station in Machilipatnam, which was studying a great cyclone that was coming. So he somehow convinced the authorities that I want to go and work on that cyclone stuff. But in between, he also wanted to observe the eclipse. So this is very dramatic, and like this is August, because this is monsoon month. And with an eclipse, you have no control over it. This is not a laboratory. If the sun is covered with clouds and it starts raining, you're done. All these 9 years of waiting, flying all the way from, I don't know, not flying, I guess, at that time.
They would have taken a ship back then.
Yeah, coming all the way from France, all of that would go to waste. So you can imagine the passion of these people and the conviction and the, urge to know about this, urge to touch this. And the amazing thing is that they looked through their telescope, and there was good, though there was morning mist, and there were some, some things were not functioning and all that. They actually managed to take data, and look through their spectroscope and analyze it. And they saw exactly what Bunsen and Kirchhoff had predicted. All of them, making independent observations, all of them saw the appropriate bright lines in the exact location of the Fraunhofer dark lines, the reversal that Kirchhoff and Bunsen predicted. And this is also a very important feature of science, that you don't just do an experiment in isolated laboratory and say that I've seen something, and this is the truth. You have like multiple people repeating the experiment and, convincing themselves further and further. So all these people, and it was just so amazing that they saw exactly what they were looking for. So, and this is a picture that was taken in 1859 by Tennant, actually. And as you know, how many of you have seen, so many of you might have seen the totality. I've never had the good fortune of seeing a total solar eclipse in person, only on TV. So this is a picture from 1859 that Tennant had taken, and it's pretty good. You can see the corona, and now you see exactly what they wanted. Like the entire disk is blocked, and only the outer layer is visible, and light from that, whatever light they were seeing, was light from that area. That is exactly what they wanted. And as a matter of fact, this I found on Amazon, that this is even available on Amazon. The report on the total eclipse of the sun. Here they say August 17th and 18th. I might have gotten the date wrong. Yeah. So as observed at Kuntur. Yeah. So maybe I got the date slightly wrong. Okay, so now Pogson in Machilipatnam, what he did, this is the actual picture of his, he observed the spectrum and he drew a hand-painted picture of it. And this is that picture. And and here you can see that the bright line is exactly coincident with this dark line here. And you can see, the reversal. And this is this picture is kept at the archive of Indian Institute of Astrophysics in Bangalore. It's taken from there. Now, everything was fine. It was a very exciting discovery. And I told you about this sodium, right? The sodium had the dark lines of sodium came, and this Fraunhofer named them D. So, and actually it's a line out here in the middle of the yellow. And really, it's like two lines. They call it the doublet of sodium. Very closely spaced two lines, both coming from sodium out there. So it's a very, very famous, strong line of sodium, which is called the sodium D line. Even when I was in my MSc Plus, we did experiments to observe the sodium D line. So whatever they saw in this spectrum, they thought that it is coming, both Tennant and Janssen thought that what they saw here in this light coming from the corona, they saw it's very close to, it is sodium, it's right there. Only Pogson had a little bit of doubt. And he said he observed that the new line was either, so he wrote that it's either coincident with or very near the well-known sodium D line. And those two doublet lines were called D1 and D2. Some called it the D3 line, this new line. And there was a lot of, most they say that's very close to sodium, it must be sodium, so what's the big deal? But Pogson had his doubts. And that doubt proved to be something very, very remarkable. Led to a very new, unexpected discovery. So Lockyer's idea was different. So he had planned, he said, like, I'm not going to go chase eclipses. He had planned to focus on there are things called prominences on the sun, which I'm not going to get into details of. They're like bright spots, and which people knew that they were on the surface of the sun. They were on they're anchored to the atmosphere. So they said that, so he said, like, if I can move my telescope and somehow, even without an eclipse, I focus on light coming from that prominence, since I know that the prominence is on the outer atmosphere, I'll isolate light from there and see the spectrum from there. That was his idea. So Janssen, once he'd observed the eclipse out here, he was, jobless, and he thought, like, the next day, he knew of Lockyer's idea. So he thought that, now that the totality is gone, I will also observe a prominence. So he, I think instead of 18th, I wrote 8th. So that is a connection. So it was September, no, that's wrong. August. So whatever the eclipse day, the day after the eclipse, he again looked at the sun, but now he focused on a prominence, and he again found that same new D3 line, from a different. So he did more observations, and he sent a detailed report on September 19th to the French Academy of Sciences. Lockyer had some bad luck because his telescope maker, I think, fell sick and couldn't deliver the telescope on time. So he couldn't get to test his idea until October 20th. Now, this guy sent it off report to the French Academy on September 19th from India. So those days, no regular, WhatsApp, email. So it will go by regular mail, and it took a long time to go. On the other hand, Lockyer was in England, and all he had to do, so he looked at the telescope and he got results identical to Janssen's spectra, including the that near sodium line. Now they were convinced that this is not sodium, this is a new line. And what could it be? It must be due to a new element. And Lockyer, since it's coming from the sun, and the Greek name for sun is Helios, he attributed that line to a new element and he named it helium. Yeah? And so then he got his telescope only on October 20, tried this out, got the same results, mailed his results to French Academy. And since it was close, it was Europe, right next door, it just so happened that these two letters, reports from Lockyer and Janssen arrived within hours of each other, one from India, one from England, but the same day, to the French Academy. So they were given, so this is the, whatever that middle, they were given joint credit for discovering a method analyzing the solar spectrum without an eclipse, because they did it, not the credit for discovering helium. So the discovering helium is a little tricky, and whatever you see on the internet is not completely correct. The credit, because Janssen did not quite recognize it as helium, Lockyer did, though the credit is given to Janssen, and Pogson and Tennant's names are just washed out of the picture completely on most of the sites that you see. Yeah? So now, before that, let me ask, like, all of you have seen, of helium balloons, right? Do you know of helium balloons?
Yes, ma'am. The balloons that float.
What is special about helium balloons?
They
can
keep on
fly.
It sounds squeaky.
Helium is one of the lightest types.
They go up very high, right? So helium is very low density, very light, right? So this is helium. So can you think of a reason why all the other elements were discovered on Earth very easily? Why was helium not discovered on Earth? Actually, the first discovery of helium came from the sun. So this was the first element, first and only element that was not discovered by chemists, but discovered by astronomers. Why was it not discovered on Earth? Yeah. Manvik.
Yes, ma'am. As we know that helium is lighter than air on Earth.
Yeah.
Because of that, because of
Yeah.
the buoyancy, it basically floated up and went in the very extreme upper part of the atmosphere.
Okay.
So that's why we find it.
That's a very good answer. And I'm not going to take all the answers. I'm sure you have like similar ideas. So that's one of the reasons that helium is very light. So it doesn't stay, Earth gravity cannot really bind it very easily. Secondly, helium is if you learn a little more chemistry later, it's an inert gas. So it doesn't form compounds very easily. So it's not, you cannot find it in compounds on Earth, unlike, other elements. Yeah.
Yes, ma'am.
So, but finally in 1895, 27 years after it was detected in the sun, helium was discovered by, oh, I have a by also there. In the mineral cleveite by Sir William Ramsay in London, and independently by Cleve and Nielsen in Uppsala, Sweden. And it showed the same line. As I said, that the spectral lines are a signature, a fingerprint of the element. So whenever you see a D3 line in that position, it means that it's the presence of helium. So they saw, and people were seeing in the intervening years, they were seeing helium in all different places. From the emission of light from the Vesuvius volcano explosion, from nebulas in the sky, various things. So that I'm not getting into the detail. But the thing is that, like we said, helium was the only element to be first detected by astronomers and not chemists. So spectroscopy of solar light led to this accidental and momentous discovery. So we found helium. Not only did they confirm Bunsen Kirchhoff's theory, they also, in the process of that observation, they also, which they were not looking for, and this is something that happens in science all the time. There are also accidental discoveries, but the full, power of the method was this spectroscopy, looking for, characteristic fingerprints of elements in the spectrum. So you
Ma'am.
see that, yeah.
So, ma'am, so they use the spectroscope and try to find the D3 line and find the helium on Earth, or
Yeah,
did they
yes.
find it
Oh,
on
yeah,
other?
yeah. Again, they use the spectroscope, similar spectroscope. By that time, 27 years, spectroscopes also must have been developed much further, better, and all
Yes,
that. But they again, basically they took that whatever that light was coming, and they looked at, from that mineral, they looked at the spectrum and they found this line. Yeah. So, and of course, these guys had to use a combination of a telescope and a spectroscope, right? Because the
yes, ma'am.
light was coming from a telescope, and attached to that there was a spectroscope, and then that's what they found. Okay. Okay. So
ma'am,
this is yeah.
So because of we found helium on Earth because of this D3 line only, ma'am.
Yeah. In the sense that you once you see that D3 line, you know that this must be helium. And basically, helium on Earth mostly comes from radioactive elements, because from
Yes, ma'am.
radioactive emissions, you get alpha particle, helium is emitted in that. But helium is
Yes,
hard
ma'am.
to find on Earth. Yeah.
Okay, ma'am.
It's
Thank
so
you.
decay of uranium and thorium or something like that. Yeah. Okay. So, but everything I know about this comes from a friend of mine, a good friend, astrophysicist friend of mine, who has studied this whole story in great detail, and he's written a book on it, and he's also got very nice YouTube lectures which you can also listen to. So he's written a book called The Story of Helium and the Birth of Astrophysics. So Biman is an old friend and an excellent astrophysicist. So credit goes to him for teaching me this. I learned this stuff from him. Okay. Now just a little more to go. So now we found that it was possible to detect the presence of various elements in the stars through spectroscopy. Like now we know, like whatever is coming through the atmosphere, what is the atmosphere made up of? You look at the spectrum and say these elements, because these were the missing lines. And and every time now you don't want to always look at it. You don't need to find eclipses and stuff like that all the time. All you do is look at the solar spectrum coming from a telescope, look at the dark lines and find out which elements correspond to that. That's all that you need to do. And by the way, Fraunhofer did a very excellent job at that time to find the dark lines. But now, of course, instruments have become, more and more sophisticated. And now there are thousands of more dark lines that have been discovered by astronomers or chemists or whatever. And so all of those correspond to the whatever. From there, you can find the composition in greater detail. But that is which elements are there. So that's telling you that. But then you can ask more interesting questions. For example, that, okay, there are elements in the star. I know that there's helium, there is hydrogen, there is a little bit of sodium, this is a little bit of carbon, whatever, but oxygen. But how much of it is there? That, how do we know that? And it turns out that all we have are the spectral lines. And even that information is in the spectral lines. You just have to know how to decode that. Yeah. So the next, so this is I'm just showing you a graph. You don't have to look at the details. So this is like this is plotting the intensity versus wavelength. So this is telling you like, how bright or how dark roughly the lines are, and then how dark, how bright, the amount of light getting through in that region is sort of telling you like the relative abundance. So that's roughly the technique that you use. Right? Okay. Now I'm going to move to fast forward to the 1920s. Is this blocking the thing? I don't know. Is this blocking?
No, nothing's blocking,
Yeah.
we can see.
Okay. Yeah, so I'm going to fast forward to the 1920s.
But Sukanya, we also have like 5 minutes left.
5 minutes left. Okay, so this will go with that. Yeah. So, so this I will like fast forward through this also. That so here all the discoveries that I talked about were made by men. You know, like there were no women on the scene at all. And here I would urge you to look at these two women, especially the one on the left. This is Annie Jump Cannon and Cecilia Payne Gaposchkin, who made like momentous discoveries. Annie Jump Cannon was a little older. This was like late 1800s. But the point is that this was 1920s, so physics had also progressed a lot further. You know, like quantum theory was born. We understood why the discrete lines happened due to jump of electrons and all of that. I'm not getting into those details. And not only the sun, the spectra of thousands of stars, starlight telescopes had become more advanced, so were analyzed. And now this was a bewildering, profusion of data. And this lady, Annie Jump Cannon, she, in Harvard, so in 1894, she began the project of examining the stellar spectra connected by the Harvard Observatory. And she was, I mean, I'm not getting into the details. So she looked at thousands of photographic plates and arranged them in some order, you know, like classified the spectrum, right? So all of that. And they knew the composition was also like roughly known, that kind of thing. So this is what Cannon did. Cannon's data was there. Then there was Cecilia Payne Gaposchkin, who was graduated in Cambridge, and those days women were really discriminated. She was an excellent student. She graduated with excellent grades, but she was not given a degree because Cambridge did not give degrees to women, you know. So from there she came to America, to Harvard, and she started looking at it. She knew a lot of the new physics, the quantum physics that she learned in Cambridge. And she looked at Annie Jump Cannon's data and combined the data with the quantum theory that she learned in Cambridge. Plus, again, there is an Indian connection of a very important physicist, Meghnad Saha, who did some work on, which is spectra of stars, you know, like how to connect the temperature and the spectrum, you know. And she put all that together. And what she did, combining Saha's work with that, she correlated Cannon's classification of the stars with the temperatures. You know, so temperature was an aspect that was not explored. You know, like this, you see that this star is giving this spectrum. That characteristic spectrum also had a connection with temperature. Then she looked at the abundances and she discovered something very spectacular. You know, until Cecilia Payne's discovery, people thought the composition of the Earth and the stars were roughly the same. You know, like whatever elements were found on Earth, same in the stars in the same proportion. And what she found was that hydrogen is 1,000,000 times more abundant, and helium is 1,000 times more abundant than all the other elements in the stars. And this was such a momentous discovery that other people did not believe her. And when she submitted her PhD thesis examiner, very fine as astronomer, Russell, told her that, you know, you found this data, please write down that this is probably wrong. So she was forced to write down that this is probably wrong. And then a few years later, Russell himself found the same data, and then it became, you know, like a well-known theory. And she did such amazing work, and she got credit for it very late in life. She became a full professor in Harvard only at the age of 59. That's a whole new story altogether. But look at the composition. That in this pie chart, essentially the other elements you cannot even see. They're so tiny. They're like 2%. And the bulk of the star is composed with hydrogen and helium. Most of it is hydrogen. So this is what Cecilia Payne-Gaposchkin's path-breaking work was done, not only finding out what elements were there, their proportions as well. So, and I'm coming to the end. And now again, like, what to do.
Sorry, Sukanya, we have to wrap up soon.
So here, this is not only the stars, even in the entire universe, this is the proportion of. So now, notice that visible light is only a tiny part of the electromagnetic spectrum. So, so it's only a tiny part of the electromagnetic spectrum. Each wavelength offers, like radio, infrared, ultraviolet, X-ray, offers a new window to probe the universe. So there are plenty of treasures yet to be discovered. So that's where I close. And I just want to, I can share later, and you can actually build your own spectrometer from an old CD, and there's a link for that. And what you can test, you know, various light from the sun, light from tube lights, whatever sources of light you have in, and you can try it out. You'll have your own way of generating a spectrum. So I think.
Can you share this link in the chat?
Siddharth will share it.
I'll email it to everyone by tomorrow.
And there are plenty of, if you even search on, so let's stop share. So search on the internet, you will find plenty of these, you know, links to build this spectroscope, just from a serial box and an old CD. So it's very, very cute, really. Yeah. Okay.
Thank you so much, Sukanya. Sadly, we're out of time.
Out of time.
I will just quickly give a short overview of what's coming, like the upcoming events, and then we will wrap up. Let me just share my screen.
So if you have any other questions, you can send it to me later, and I can, you know, connect with Siddharth and.
Yes. Yeah. So today we saw we had this great masterclass, and thank you so much, Sukanya. I was actually feeling like very excited when you said that they found it, and the same people, like they found the exact same things. You really told the story in such a way that took us all together. So thank you so much. Then on 29th June, that's 2 weeks from now, Ashish Kulkarni, who's an economist, is going to be talking to us about how everything is connected to everything. This is in part going to be a quiz kind of event. So do come with your quizzing hats on. And even if you're not interested in quizzing, I'm sure this will be a fascinating session for you. And then a week after that in July, Murli is going to be leading a session on paper structures and soft robotics. So he's going to be using materials that you have around in your house and teach you how to explore engineering through that. Now, part of this, all of these people are connected to upcoming residential summer programs. If you'd like to know more about this, just get in touch with us. So from July 10th to 31st in Manipal in Karnataka, for students who finished grades 7, 8, and 9, they can choose between a whole bunch of courses that happen over 3 weeks in a residential setting. And students who finished grades 5 and 6, there's a 2-week program, one which is focused on the pleasure of finding things out, and a second on the joy of creating things. I'll be teaching module 1, and another mentor will be teaching module 2. Then in July, at the end of July and into August, Sukanya and Murli will be teaching for high school students a module on astrophysics and a module on engineering design. So this is available on the Gifted World website. If you just click on the events section, you can see all of this information, and do get in touch with us if you want to know more. There's a question about the next fortnightly challenge. Sorry, we've been delayed in giving out the answer to the previous one and setting the next one. We will certainly do so over the next 2 to 3 days. And with that, I thank you all for being part of today's session. Sukanya, if you'd like, I have to leave, but I can make you the host if you'd like to stay for 5-10 minutes and listen to people's questions. Or...
That's okay. Yeah, I can see if people have questions. Yeah.
Yeah.
If they want to, whoever wants to hang around a little more. Yeah.